Cool, Daniel here. We're back to maps. Let's practice them. All right, first exercise. We said that maps map keys to values. That means there can be only one mapping for a key at any given time. But question for you, what would happen if in the lowercase map here, if I had two original entries like Jim to 555 and Jim with all caps, let's say 900 or 9000 or something like that, and I ran this little guy over here, what would happen? Non-trivial question. Now let's design an overly simplified social network based on maps. All right, so each person will simply have a name. So person equals basically string. The network will keep an association, that is a map hint, between each name and a list of friends. So basically to another list of strings. We want to be able to add a person to the network, remove a person, friend, which basically means that a person adds another as a friend, and friendships are mutual, and unfriend, again mutual. We also want some stats. For example, number of friends of a given person. The person with most friends. How many people have no friends? So they're just joined the social network without actually having friends. And also want to say if there is a social connection between two people, direct or not. That is, if I know you and you know someone else, then there is a social connection between me and that someone else. That's what I mean. So pause the video and try to work through these exercises. They are pretty simple, but I want you to get accustomed to using maps. All right, so I'll be back with some solutions after breaking. So exercise number 1. What would happen if I had two original entries, Jim and capital Jim? Well, I only need to actually add them to phone book and see what happens. Let's say we have JM caps and 9000 or something like that. So let's right click and run and see what happens. So first of all, the Jim and the Jim keys are properly added to the map, so that's not a problem. But when we get into the lowercase, we have right over here Jim 9000 and Daniel 789. Well, that's a problem because both Jim with capital J and Jim in all caps overlap now in the resulting map. Now, the lesson here is that you should make sure when you map your keys that the resulting keys do not overlap, because otherwise you might lose some data. All right. So I'm going to put in some exclamation marks here. So careful with mapping keys. Now let's talk about this overly simplified Facebook right over here. So our entire social network is basically going to be a map from string to a list of string. All right, so let's add a person to the network. Def add. And I'm going to pass in the network, which is a map from string to a list of string, and a new person, which is a string. The result is going to be a new map from string to list of string. And the implementation of that is going to be very simple, and that's going to be, what have I done? Nope. So the implementation is going to be network plus. So this is how you add a new pairing. Our purpose here is to add a new pairing between person and an empty list. So person, arrow, list. And I'm going to put these in parentheses so that it doesn't confuse the compiler. All right, so this is adding. Removing is more complicated, so I'm going to leave that later. Let's define a method called friend. This is always going to receive the network, which is a map from string to a list of string. And say person A and person B. Let's say A, which is a string, and B, that's a string. The result is going to be map string to list of int. Okay. So, first of all, I need to retrieve the friend list of A and the friend list of B, which is network applied with A. Now, I'm going to take the responsibility of getting errors thrown in my face. That's not the purpose of this exercise. The purpose is to just use the map functionals. Okay, so we can simply guard against these with tries, but again, this is beyond the scope of this exercise. So continuing, friends B equals network B applied to B. I could also call this friends A, of course. Right, so the end result is going to be network plus. And to A, I'm going to associate friends of A with B appended to the list. Now the compiler complains because I haven't put these in parentheses. All right. Then plus B arrow, same thing, friends of B, colon plus A. Now, we're not going to deal with duplicates here, so if I friend with A and B twice, I'm going to add these guys twice in their list. Let's actually use the set type instead throughout the entire implementation. Okay, and instead of colon plus, we can simply use the plus operator. So for sets, if I say set plus a value, then that returns a new set with that element added. And using sets guarantees that our list of friends only contain unique elements. All right, so this is friending. Unfriending receives a network, just a map of string to set of string, and say A, which is a string, and B is a string, and the final return type is map of string and set of string. The implementation is going to be very similar to friending, so I'm going to copy this over, and I'm going to say network plus, and to A, I'm going to associate friends of A minus B. So the minus sign is an operator which operates on a set and removes the element B from the set. And plus, and to B, I'm going to associate friends B minus A. So notice I'm always using this plus operator between the map and all these pairings. So the plus actually creates a new pairing in the map. So where there was an old pairing, if I say network plus this new pairing, that will replace the old pairing with the new pairing in the result. And finally, let's talk about remove. This is very complicated. So network, which is a string, to set of string, and we remove the person, which is a string. The end result is a map of string to set of string. We'll need auxiliary functions for that. we can't simply remove the key person from the map because this person might have friendships, and those friends will have some dangling friendships to an inexistent person. So we'll have to remove those friendships first before we remove the person as a key. So we'll define an auxiliary function. Let's call this remove aux, which receives a list of friends, which is a set of string. These are the remaining friends who need unfriending the person. All right. So we'll store that in an accumulator, which is a map of string to set of string. And the result is a map from string to set of string. This is a plain old tail recursive function, which will go through all friends and remove them from the network. So if friends is empty, then just return the accumulator, network ACK. Otherwise, we need to unfriend person with one of the friends and call remove aux recursively. So we call remove aux from friends tail, and unfriend with the accumulator in the current state, so network ACK, and we unfriend from network ACK the connection between person and friend's head. So basically we take the first element from friends, we do an unfriend between person and that guy, and then we call remove aux with the remaining friends. Okay, so not quite trivial. So first, we need to do unfriends. Let's call this unfriended equals remove aux. And the friends are going to be network applied to the person. So this person's friends. And network ACK will start with the network value. Then, from this unfriended, cleaned map, I am simply going to remove the person. So unfriended minus person. The minus method just removes the person key entirely. But right now, I'm safe to do that because all the dangling friendships are gone now. So let's go ahead and test these before we go in and define the stats methods. So if I create network. Let's call this empty, which is a map from string to set of string. Then this will be a new map. Now let's add a couple of people to this network. Let's say Mary and Bob. So let's say a non-empty network. And that is, we call this add. All right. So add with network or empty and a new person. Let's call this Mary. Okay. And let's add another person called Bob. So let's add empty Bob and then Mary later. All right. So if I print line this network, network, then I should see two associations between Bob and an empty set and Mary with an empty set. All right, cool. Let's make these friends. So if I say friend, network, and Bob and Mary, then these associations will have Mary for Bob and Bob for Mary. So if I run this again, look, I have Bob with set Mary and Mary set Bob. So Bob has a friend called Mary and Mary has a friend called Bob. Let's remove their friendship. So print line, and I'm going to copy this and I'm going to do an unfriend with friend, network, Bob, Mary, and then Bob, Mary, or I can specify them in the reverse order because it doesn't really matter. Bob will be removed from Mary's friends and vice versa. So this will keep the old associations. So the unfriend method also works correctly. So now let's try to remove Bob altogether from a friended network. So I'm going to call remove from this network with Bob and Mary friended. And let's just say I remove Bob entirely. So I should be seeing only this association with Mary instead of nothing. Because prior to removing Bob, I remove all his friendships, right? So I'm left with a clean network. So all of our methods seem to work. Now, you might notice that these methods right over here and this way of building a social network is quite cumbersome because whenever I want to add two members, I need to call add twice, which is a bummer. But a better design would be to just move these methods to their own class, right? But this is beyond the scope of this exercise. I want you to get accustomed to using maps. So let's build a small network with Jim, Bob, and Mary. Bob and Mary are friends, Bob and Jim are friends, but Jim and Mary are not. So that will be, let's call this people, which is add called twice, actually 3 times, and Jim. So Bob, Mary, and Jim. Then let's call this Jim Bob, which is friend, not print line, but val. It's basically in my reflex now to print line everything. So call friend with people with Bob and Jim. Now we call this with Mary Bob, which is friend with Jim Bob and Bob Mary. And this is our network. Let's call this testnet. All right, so let's print this out just to see that our relationships work correctly. So we have, for Bob, 2 friends, Jim and Mary. For Mary, just Bob. And for Jim, just Bob. Now, let's write the other methods. So we said that we wanted to find the number of friends for a given person. So n friends. And this will receive a network, which is a map from string to set of string, and a person, which is a string. Okay, and this will return an int. Okay, and the implementation is going to be fairly simple. So if not network.contains the person, right? So the person is not part of the network, then I'm just going to return 0. Otherwise, I'm going to get network apply, or network applied to person, dot size, without unnecessary parentheses. So network applied to person will return the set of their friends, and I'm going to call the size method on that set, which is fairly simple. So if I print line n friends with our testnet, and who has more friends? I think Bob has more friends. Then let's see what this prints out. And it'll print out the number 2 because Bob has 2 friends. All right, so the n friends method works nice. All right, let's write, what do we say? Person with most friends. All right, let's say most friends. And we pass in a network, which is a map of string to set of string. And this guy will return a string, which is the person with the most friends. And this is a trick. And we'll return network dot, and this is a method specific to maps, which is max by. And this receives a lambda from a pairing to a value. And the value has to be comparable. So we'll return pair._2, which is the list of friends for every pairing, dot size. This will return the pairing with the maximum value given by this lambda, and then we'll return _1, which is the key or the first element from that pairing. So if I go ahead and print line most friends from the network, then I should be seeing, I think, Bob. Bob has 2 friends. All right. So most friends also works well. What do we say? How many people have no friends? Okay. Let's see. N people with no friends from the network, which is a map from string to set of string. And this returns an integer. Although probably not trivial to think about, this function is also pretty simple. So it will say network, and I'm going to filter. I'm actually going to use filter keys, where for every key, network applied to that key dot size is equal to 0. Okay. And then I'm going to call size. So this is the number of pairings in a map resulted from network by filtering the keys whose network k.size is equal to 0, which the ID suggests that I use is empty instead. So again, the implementation is going to start with a network, and it will filter the keys for which their friends list or their friends set is empty. And then I'm going to call the size method to determine the number of pairings in the resulting mapping. So if I try to print line and people with no friends with network, I'm going to probably see 0 because every single person in this network has friends. So I get 2. Why do I get 2? Oh, that's because we tested with the network and not with testnet. And also testnet here. But the value Bob here is not going to change. So if I right-click and run this again, good. I still have Bob, but now I have 0 people with no friends, which is good. Now, there are alternative ways to actually compute this. So instead of filtering keys, I can actually filter pairings. So I can say pair by pair._2.isEmpty.size, right? So instead of filtering keys, I filter pairings, and for each pairing I test their _2, which is the list of friends, and I test that for isEmpty, and I call size. And the IDE is smart enough to tell me that I can replace filter.size with a count. So there is an actually shorter way to do that by replacing filter and size with count. And for every pairing, I test whether pairing._2.isEmpty holds true, and the count method will actually count all the pairs for which this lambda will return true. An even shorter way to write this, if you are versed in the shorthand lambda syntax, is to simply write _._2.isEmpty. This is extremely shorthanded, and sometimes it's hard to read, but in this case we just want to play around. So this is an alternative implementation which is extremely short. If I right click and run this, I'm going to see the same result. And finally, the hard function, the social connection, which receives a network, which is a map from string to set of string, and say person A, which is a string, and person B, which is a string. And the final return type of this function will return a Boolean, because we simply want to test if there is a social connection, direct or indirect, between A and B. We'll solve this by running a breadth-first search in our graph. This is computer science A, and we are going to do that by creating an aux method inside. So let's call this BFS. And we'll pass in our little target, which is a string. We'll get a list or a set of considered people, which is a set of string, and a set of yet to discover people. So discover people, which is a set of string. And the return type for this BFS is going to be a Boolean. And the significance of this function is going to be, can I find a target in discovered people having considered people already? All right, this is a hard function to think about, but the implementation is going to hold just a few lines, so not more than 5 lines of code. All right, so the implementation is going to be the following. So if discovered people is empty, then I have no set of people to search in. So I haven't found the target and I cannot find the target. So I'm just going to return false. Otherwise, let's just consider a person out of discovered people. So discovered people dot head. If this person has already been considered, so if considered people dot contains person, then I'm just going to call BFS with the rest of the discovered people. So BFS with target, the same considered people, and discovered people dot tail. Otherwise, if this person happens to be equal to my target, then I found it. I'm just going to return true. Actually, it makes more sense to put this first and this condition later. So else if, and remove the extra if. So if this person is equal to target, then I'll return true because I found it. Otherwise, if the considered people already contains the person that I'm looking at, then I'm going to call BFS recursively. Otherwise, I'm going to call BFS with the same target, and this person has already been considered because I've looked at it and it's not equal to my target, so I'm going to add it to considered people. So I'm going to say considered people plus person, and the rest of the discovered people is going to be discovered people.tail, but I'm going to append all this person's direct friends. So I'm going to say network applied to person. So quite a heavy implementation here, even though it's only like 5 or 6 lines of code. And finally, having done the BFX aux function, I'm just going to return the call of BFS, that my target is B. So in A's direct or indirect descendants, I'm looking for B. Considered people is going to start with an empty set because I haven't considered anything yet. And discovered people is going to be A's direct friends, so network of A, plus A itself, because it might be the case that I might call social connection with A and A. All right. Now BFS, if you've noticed, is a very nice tail recursive function. Okay, but it's pretty heavy, so take a minute or two to look at this implementation and figure out why this makes sense, run some diagrams, and break it down. All right. Okay, so I'm just going to print line here, social connection with our testnet, and I want to see if there's a social connection between Mary and Jim. All right, so testnet, Mary, and Jim. So right click and run. Hopefully this returns true. Yes, it returns true. But let's take the other network, say network with Bob and Mary are not friends. So if I do social connection with network and Mary and Bob was it, right? Bob. Okay, so it's Bob. So this guy should return false. Yes, it returns false. So just for our simple test cases, our social connection function works well. This was very difficult. You're now getting into true functional programming. Now you're talking. I'm Daniel, and I will see you very soon in the next videos.